How do overcurrent protection trip curves work? Imagine a safety net for electrical systems that catches problems before they cause damage. That's what overcurrent protection trip curves are all about. They show how circuit breakers respond to different levels of current over time. When current flows through a circuit, it should stay within safe limits. But if it gets too high, the breaker needs to trip and disconnect the power. The trip curve is like a map that tells us how quickly that happens at various current levels. It balances protecting the system with avoiding unnecessary trips during normal operations, like when motors start up. At the heart of trip curves are two mechanisms. The first is the thermal trip. It uses a bimetallic strip that heats up when current flows for a while. If the overload is only slightly above normal, the heat causes the strip to bend and trip the breaker after a delay. This slow response prevents trips during brief overloads. The longer the current stays high, the more the strip heats up, and the sooner it trips. This part of the curve is called the long time trip, and it has an inverse relationship between current and trip time. The higher the overload, the faster the trip. The second mechanism is the magnetic trip. It reacts almost instantly to very high currents, like short circuits. It uses an electromagnetic coil that activates when current exceeds a certain threshold. When that happens, it pulls a trip mechanism within milliseconds, opening the circuit immediately. This instant response protects the system from severe faults. The trip curve is plotted on a graph with current multiples of the rated current on the horizontal axis and trip time on the vertical axis. The curve shows a tolerance band, meaning the breaker will trip within a certain time range for a given current level. Different types of trip curves are used depending on the load. For example, Type B trip curves trip between 3 to 5 times the rated current, ideal for resistive loads like lighting. Type C trips between 6 to 10 times the rated current, suitable for moderate inrush loads like small motors. Type D trips between 10 to 15 times the rated current, designed for large motors with high start-up currents. Choosing the right trip curve is vital in power systems and renewable energy setups. Motor circuits need curves that tolerate start-up inrush without tripping, while sensitive electronic circuits requiring faster trips to prevent damage. Advanced devices like inverse-time overcurrent relays use mathematical formulas to calculate trip times based on current. These calculations help coordinate protection devices upstream, ensuring selective and reliable operation. In summary, overcurrent protection trip curves work by defining how quickly a circuit breaker trips at various overcurrent levels. They combine a slow thermal response for overloads and a fast magnetic response for short circuits. Proper selection and coordination of these curves keep electrical systems safe and running smoothly.